All right, we are live. Audio and video is up. Welcome back to Statics. We are in lecture 28. Wow, it is. We are rocking and rolling here. Today, what we're going to do is we're going to talk about centroids again. I want to talk about some additional applications. I want to look at centroids of lines and curves, and there's some reasons why, and you'll see that here in a bit. And then I want to start to tie into some other applications and some stuff that I want to deal with when we start looking at structural analysis. And so I want to go back to support reactions. This is what we did in exam 2, where we were looking at you have a beam and a series of point loads. What are the support reactions? But I want to talk about distributed forces and how centroids and the concepts of centroids are vitally necessary to determine those types of support reactions and do that analysis. But first off, let's just recap. So we've introduced two terms: the center of gravity and the centroid. Remember, the center of gravity is sort of your weighted average of your weight, and the centroid is the weighted average of your area. And there's two ways you can go about it. You can use a calculus-based perspective, and so, for instance, if we're talking about the centroids, let's say we're looking at this application down here. What we're doing is we're integrating the area and integrating the first moments of area, and then using that to define the centroid. And that's fine if you have a shape that isn't comprised or can't be adequately represented by a series of or a collection of simple shapes. In a lot of practical applications, what you're dealing with is, the shape is complicated, but you can break it up into rectangles and triangles and circles and all of that stuff. And if that's the case, just use your basic algebra-based definition to compute the centroid. And they're both essentially the same thing, just one is using differentials and one's using incrementals, I guess would be the way of putting it. Now, I guess the one thing you do need to have with you is a centroid reference. Some of these, you can probably remember, like the centroid of a triangle. I think most of you will probably have that memorized by the time you graduate with your engineering degree, because you'll use it so much. And then there's some other shapes like circles and rectangles where it's evident, it's easy. Some of the other, I say more funky ones like parabolic sectors or ellipses and things like that, I'll be honest, I don't remember those offhand. And so for shapes like that, I need a reference. And there's oodles of these types of references available. They're in your statics textbook. You can Google them. For instance, those of you who decide to take steel design, open the steel manual. They're in there as well. So they're not hard to find. What I want to do is expand on this a little bit, and I want to talk about some different applications. The first thing I want to do is I want to talk about the centroid, or the center of gravity of a curve or a line or a series of lines. So just as before, where we determined the centroid and the center of gravity of an area, of a two-dimensional area, we could determine the centroid and the center of gravity of a one-dimensional object, a curve. And then so on Friday, what we'll do is we'll look at the centroids of three-dimensional objects, like what's the center or the centroid or the center of gravity of a body, of a three-dimensional body. But today I want to look at one-dimensional objects. And so one thing you might ask is, like, when would you ever want to find the centroid of a curve? Like, in what real-world scenario would that matter? Well, there's a lot of scenarios where that matters. When I was putting this together, one of the scenarios I thought of, my wife and I, we were watching a show on something like the DIY Network or HGTV, like one of those, Mike Holmes home repair shows or something like that. And they were doing some remodeling of a given house, and they were working on the roof, and they were basically replacing the roof and putting a brand new roof, and not just the shingles or the sheathing, but they were actually erecting a new structure to the roof, a new roof truss. And so if you've ever done or seen any type of residential construction or worked on anything like that, you know, your roof truss is just a triangular arrangement of wooden joists that support your roof. And like on my house, I have a pretty simple house geometrically, and so the roof trusses are really simple. They're just a simple triangle. But this house was different. The roof trusses they had a very weird geometry, and when the crane was picking them up and trying to set them on the roof, because the trusses were of this very irregular geometry, as the crane was picking them up, they were kind of wobbly, and they were hard to manage, and they were hard to lift. And I saw that, and I went, oh, they need to know where the centroid of that truss is so that when they pick it up, it stays stable. And I thought, man, that's a perfect example to mention in statics. But there are some other applications as well. So I'm a steel design guy. That's my area of expertise, is steel design. And one of the things that we deal with in steel design is weld groups. So you have a connection in a steel structure, and you have, let's say, a bead of weld. Let's say it's a C-shaped weld that connects a member to an adjacent member. Where is the centroid of that weld group, so that you know what are the shears and tensions and things like that on the weld elements. And that's incredibly important. And basically what we're doing is the exact same thing, although if we're talking about the centroid, you know, for a region, we might say X bar is the sum of AX divided by the sum of A. Because we're dealing with a curve, we're not talking about the sum of the areas, we're talking about the sum of the lengths. So we say the sum of X times L divided by the sum of L. So it's basically the same process. We're just looking at it sort of one-dimensionally, if you will. And so you could probably guess where this is going in 3 dimensions. So if you were trying to find the centroid of a 3-dimensional body, it might be the sum of X times the volume divided by the sum of the volumes and whatnot. So, I keep wanting to use my eraser there, but that doesn't work on the drawing here. So what I want to do is I kind of want to walk you through how that works. I want to look at the centroid of this. It's basically, we have a wire. This is a one-dimensional wire. Imagine this wire has been bent into this this triangular region that you see here. So one of the things that we're going to do, I wanted to make a couple statements about this. We are going to assume that the wire is made of a homogeneous material. What that means is that the center of gravity and the centroid are going to be in the same spot. So that might not be the case if the wire got heavier on one end as it did on the other. Or, and this is a very real possibility, what if, you know, let's say if we were talking about a truss, what if one member was made of steel and one was made of aluminum and one member was made of wood? Well, then the centroid and the center of gravity wouldn't be in the same spot, because each wire would have a different weight. So you'd have to, so if you wanted to be accurate, you'd have to reference your center of gravity in terms of weight, not in terms of lengths. But because this wire is all made of one material and it's homogeneous, we can say that they're at the same spot. Another thing that I'm going to mention right off the bat is you can see the wires are kind of like rounded right here. We're going to just sort of neglect that for purposes of the problem, and we're just going to say that it's a straight line, straight line, straight line. And so what is the centroid of the wire region? And I'll go ahead and tell you, if you're thinking, well, that's just a triangle, it's just a third over and a third up. Not necessarily, because we're not talking about the region, we're talking about these straight line segments. All right, let me stop the share and bring up the notebook. Okay, so let me get my pen ready. Okay, so I took a little bit of liberty beforehand to get some of the table set up ready. So I've already got my table drawn. And you notice I'm drawing this the same way, pretty much the same way I did before. We've got the length, we've got the X, we've got the Y. Then we've got X times the L and the Y times the L. So we're basically following the same process that we did before, only instead of referencing the centroid in terms of area, we're representing it in terms of lengths. And so I think you're going to find this is a pretty straightforward example. We're going to go through this probably, you know, a lot faster than you would expect. But again, not very difficult. One thing I do want to do with this example is I want to show you how you can make some of these calculations a bit easier using Microsoft Excel. Okay. So first off, let's let's go through this. So we're going to take each column one at a time. And again, I'll pull up the last example just to make sure we're on the same page. So this is what we did in the last example. And you can see the table is pretty much set up the same way. Maybe I could arrange it differently because I put A, X, and then A times X, then Y, and A times Y. What I decided to do here was just put all the products over on the right side, but that doesn't really matter just as long as we're tracking everything. Okay, let's deal with the lengths first. So just to make sure everybody's awake, what's the length of segment AB? There we go. Okay, all right. That's 24. The length of segment BC is going to be 26, and the length of segment AC is going to be 10. So 24 plus 26 plus 10 is 60. That's pretty easy. So we're gonna so that's the sum of the length. So this term right here, that's going to be 60 on both of those. That's pretty easy. Okay. Next, we need the coordinates, the X and Y coordinates. And so what I'm going to do is I'm going to take each wire one at a time. But this is actually bringing up a very interesting point. And I want to actually go back to a previous example because I want to make a point about this. So let me go to example 2. All right, so this is the problem we did last time in class. And if I scroll up a little bit, I want to show you something. And I want to talk a little bit about the coordinate system. So let's take a look at this problem, okay? If you notice, you see here the shape. Notice how when the problem statement was defined, the X and Y coordinate system are already drawn. Like here's the origin, there's the Y-axis, there's the X-axis. It's already been defined for us. We didn't need to deal with that issue because the problem statement said, here's the coordinate system, compute your centroid. But we don't have that going on this problem. If we look at this problem, we were just given a shape. And the shape's like, okay, here's the shape. What's the centroid of the shape? Okay. Well, what do you mean centroid? It's like, in order to express the coordinates of the centroid, we need to define those coordinates with respect to a given coordinate system. And so what that means is we need to define our own coordinate system. So I'm going to do that right now. Now, here's the thing. It doesn't really matter what coordinate system you use. You could put the origin of this coordinate system anywhere. What I tend to do is I tend to put the coordinate system at the lower leftmost corner. So I'll say, for instance, like that's the origin. So this is the y-axis, and this is the x-axis. And I tend to do that just to make my life a little easier. All the distances are either positive or zero, so it makes the math a little easier to handle. It makes the process a little easier. But you kind of need to have that coordinate system defined because whenever you say coordinates of the centroid, what you mean is here's the coordinates of the centroid measured from the origin. So without a defined origin, the coordinates of the centroid really don't mean very much. So we need that defined. Does that make sense? Again, in the real life, nobody's going to tell you that. You're going to, as the engineer or the analyst, you're going to have to figure this out yourself. Everybody okay with that? All right. Let's take each segment one at a time. Let's start off with segment AB. So that's where I'm putting the coordinate system. So somebody tell me, let's just do both of them. What are the X and Y coordinates of the centroid of AB? And what I'm talking about is if here's segment AB, I'm basically talking about the middle of that segment. If I had just that wire, I'm basically asking, where is the middle of that segment? So for segment BC, I'm talking about this point. For segment AC, I'm talking about this point. I'm talking about the center of that wire. 12x, 0y. There you go. 12x, 0y. What about BC? Okay, now, Mr. Umber said 13x, and he said 5y. I get why you're saying 13x because it's 13 this way. So this dimension here, that dimension is 13 inches, but not along the x-axis. Along the x-axis, it's just 12 inches, right? Because if I'm talking about segment BC, here's segment BC, right? Here's the coordinate system, and here's that segment. Here's the endpoints of that segment. We're talking about the middle of that segment. This is 24, 0. This is 0, 10. So the midpoint is going to be 12, 5. Now, again, that length is 13, but we're not talking about the length diagonally. It's along the x and y axis. That's a really good point to bring up. This is going to be 12. This is going to be 5. Did that make sense? That explanation? I mean, I want to make sure that's clear. Okay, good deal. All right, now AC, what are the coordinates of that one going to be? 5y, and that's 0. Exactly right. Okay, so now we can start doing some multiplication. And so for LX, I'm going to take L times the X. So 24 times 12 is 288. And somebody check me on my math and make sure I get these right. So 24 times 12 is 288. 24 times 0 is 0. 26 times 12 is 312. 26 times 5 is 130. And then 10 times 0 is 0. 10 times 5 is 50. So that comes out, this is 180, and 288 plus 312 is 600. Sarah, I heard something in the chat. Oh. Okay. Everybody with me so far? Did I have any mathematical errors there? So therefore, what I can do, let me lower that down a bit. Therefore, the centroid x bar is the sum of Lx over the sum of L, which is 600. And then the units for this, because we're just taking lengths times moment arms, this is going to be 600 square inches over 60 inches. That's 10 inches. And then y bar is the sum of Ly over the sum of L, which is 180. Better than that. Which is 3. So the coordinates of the centroid are 10 inches, 3 inches. And I guess what I'll do here at the bottom is I'll say measured from A. The A is the centroid that's the origin that we used to reference all of these distances. So that is the answer. Okay. Before I sort of move past this, I want to see if there's any questions about just the concepts. Hopefully this should be a pretty straightforward problem. This shouldn't be that challenging. Okay, I want to show you. How to do this in Excel. So, because I think that this is really valuable. Let me stop the share here. Okay, I think that there's some really good value here. Hold on for a second. Oh, give me 1 second. All right. There it goes. There it goes. Okay. Let me zoom in a little bit so everybody can kind of see what I'm doing here. So I'm going to set up the table that I just did here. Oh, let me scroll up here a little bit. I'm going to set up the table that I just used. So we have segment, then we had L. That was inches squared. LY inches squared. Okay, and we had 3 segments that we were using. We had segment AB, BC, and AC. Then everything down here was a sum. Okay, so maybe what I'll do is change the colors up here. So, change the colors so it's a little easier to see. And you don't have to do this when you're doing the calculations yourself. I just think it's kind of easier to see it here on the screen. Okay. Okay, so this is just me prettying it up a little bit. So let's see if I can remember what was going on in this problem. Let's see. AB was 24, BC was 26, AC was 10. And then what I can do is say equals the sum of that. I want to make sure that you can read that. So all I'm doing is saying that equals the sum of the all of that region, and then I'm going to use that same formula here and here. I just need to fill in those quantities. As for the locations of the centroid, we had, or the centroid of each segment, we had 12, 12, 0. We had 0, 5, 5. And so what I can do is I can say equals that times that. Say equals that times that. So I do that one formula, and then I just copy and paste it down, and then Excel takes care of everything else for me. So I can have Excel do a lot of the heavy lifting as long as I get the inputs correctly, as long as I get those values, because really, whenever you're doing a centroid problem, and this is true of whether it's lines, whether areas, whether it's volumes, it doesn't matter. Really, what matters is the weights, if you will, like in this case, the lengths, and then the X and Y coordinates of each of those components. Everything else is just sort of that rote algorithmic grunt work, if you will. And so as long as you can get those components done, Excel can take care of the rest. Did I go through that too fast, or is there anybody that wants me to sort of highlight a particular component? Because I'm happy to. We got plenty of time. I also have another formula I want to show you because I think this is a pretty slick formula. Okay. One other thing I want to show you, this is a formula that you probably have never used before, and so it's the formula called sum product. The sum product formula, what it does is, if you notice, so let's go to the LX column. What are we doing in LX? We're taking each L term times each X term, multiplying them, and then on the bottom we add them to get that 600. I could do all of this in one step by just summing up the products of all the L terms and all the X terms, and it gives me the 600. Same thing, I can do sum product of the L's and the Y's, and it gives me those. So this is another formula that you can use. You could actually not do these two columns, and Excel will do it all for you. It's a pretty slick formula. You can sort of think of it, it's kind of like it sort of works the same way a dot product works. It just takes each term, it multiplies them, and then it adds them together, which is exactly what a dot product is. So I'll highlight that, so in case anybody wants to write that down, it's just the sum product term here. Actually, let me add bigger, and what is that? There we go. That's what I wanted. So in case anybody wants to write that down, that's a really useful formula in Excel that you might not have used before. Any questions? Let me know. Am I good to go ahead and stop the share and go back to the notes? Okay. All right, let me stop this. I thought I was going to sneeze there for a second. Okay, so go through this example again. Hopefully, I think this is pretty straightforward. That's the thing about centroids. It's vitally important, but it's usually not that difficult. It's usually a pretty straightforward process. But I want to talk about some applications. And one of the things I want to introduce now, so that when we start to see them later, when we look at shear and moment diagrams, it's not such a shock, and that's distributed forces. So up until now, we haven't actually dealt with this yet, and this is the first time that we're seeing this in statics, and that's kind of, I sort of, when I started to look at this, I went, wow, we haven't actually dealt with distributed forces. And later on, at least I can say for you civil engineers, when you take like structural analysis or concrete design or steel design, we deal with these all the time. This is a really important aspect. So up until now, let's talk about, let's go back to square one with forces. I mean, when we started out this course, we started looking at the definition of forces, and we said that, a force is basically a vector that contains, a vector contains a magnitude and direction. And everything that we did, from then on, looking at particle statics, looking at rigid bodies, looking at rigid body equilibrium, all the sum of forces, all the sum of moments, all of that was built around the base understanding of how vectors worked or how forces worked. And we said forces were a single vector with a magnitude and direction. But here's the thing. If you take that concept and try and sort of apply it to real life, sometimes it really doesn't work. But for instance, let's take a look here at the image on the bottom right. This is an image of a ballroom, and you can see there's a lot of people in that ballroom. Okay, how many? You start to think, well, how much load is that? Think it. Let's just keep the numbers simple. I'm not saying each person weighs like 200 pounds, but let's say each person weighs 200 pounds just to make the numbers simple. So if I have, each person weighing 200 pounds, and there's easily, a couple hundred people in there, if not more, let's just say there's 200 people just for the sake of discussion. So 200 people at 200 pounds apiece, what is that? 40,000 pounds. So how do you model that? Do you just put a single vector that has a magnitude of 40,000 pounds right in the middle of the room? That doesn't really make a lot of sense from a physics standpoint. That's not what's going on. I don't have 200 people all standing on a single point. They're spread out over the room. Okay? So instead of modeling that as a single vector load, what I'm doing is what I would do if I was, a structural engineer, is I would model that as a distributed load or maybe a pressure load. So instead of, a single vector, I would have, this pressure load applied over the floor. And so I might have a pressure load. Maybe this is, 100 pounds per square foot, and I'd have 100 pounds per square foot applied over the given floor. And because that represents the real life behavior of what's going on. But The problem is, okay, so I've got a load representation that makes sense, but how do I take that load representation and turn it into something that I can use with my equations of static equilibrium? Well, what I have to do for that pressure load is I have to figure out two things. The first thing I have to figure out is the resultant. And the resultant isn't that difficult because that's just the total amount of load in the system. That's easy, okay? But the other part is I have to figure out where to place that resultant. And where do I place that resultant? I place it at the centroid. I place it at the centroid of that distributed load, and that will create a system that is statically equivalent to a real life model, but also uses vectors and forces and moment arms that I can then use to perform a static analysis. Now, as structural engineers, we have a number of loads that we model. Sometimes we'll model uniformly distributed loads, like you see here on this bottom sort of central figure. So, it's like a uniformly distributed. So it's like, maybe 2,000 pounds per foot or 200 pounds per square foot or something like that. It's just a constant pressure or a constant magnitude across that length. And that's very common, especially in structural engineering applications like you see here on the bottom left. We don't model each individual person as its own unique load. We say, let's just apply a uniform pressure across the entire floor. That's how we would do this for a typical structural design. There's not only uniformly distributed loads that we deal with, but we also deal with triangularly distributed loads. This image that you see here on the top right, this is the pressure distribution that you would get, let's say, on a dam. If you're looking at the horizontal pressure that the water exerts on the dam, that pressure gets higher as you get deeper. If there's anybody in here that's ever done any type of scuba diving or anything like that, you know that as you go deeper, the pressure increases. And so that's a linear pressure. The pressure at some height or some depth below the water is equal to that depth times the weight of the water, the unit weight of the fluid. So we have to be able, in engineering applications, to deal with both. These are two very common and very real applications where we would deal with distributed loads. So, for instance, let's take the situation with the dam, the one on the top right. So, what would I need to do? I would need to model this as a linearly distributed load, this triangular load, in order to represent real life. But in order to then take this and apply equations of equilibrium, I need to do two things. I need to figure out what is the resultant, what is the resultant of this entire, load, which is basically going to be the area of the triangle. And then I need to figure out where to place that load. And where do I place that load? I place it. And then now that is statically equivalent. Okay. Does that make sense? That concept? Any questions on that? I think the easiest way to sort of demonstrate how this works is with an example. So let's take a look at this example. I have a beam here that's experiencing, this is a trapezoidal load. Now, first off, let me go ahead and say one thing. This is an example problem out of your textbook. I'm actually going to do that problem a little differently than the book does it. I'm going to do it different ways, but I think it's a little bit more of a straightforward application. I have a beam, and admittedly, I'll go ahead and say that as a structural engineer, I don't know that I've ever experienced a beam that looks like this, but the exercise of dealing with loads that have odd distributions is really important to sharpen your tools and to increase your understanding of how this stuff works. So we have this beam here, and I'm going to compute the support reactions to this beam. Now, I propose there's two ways we can go about this problem. We can split this into simple components and handle each of those components separately, or we can compute the location of the resultant and use the centroid of the whole loading, and we'll get the same answer for both. And let me sort of walk you through that. So let me stop the share here and go back to the notebook. And I'm hopping around a lot today. Where's my... There it is. Let me see if that's pulled up. There it goes. Okay, let me go to example 4. Here we go. Okay, so here's the beam. Now, one of the things I'm going to do is I'm going to try and dispense with as much formality as possible. For instance, when we were first doing this type of problem, when we were learning about reactions, in chapter 4, we were being really, really formal with it. For instance, we were saying, okay, this is a roller, so it has a vertical reaction. This is a hinge, so it has a vertical reaction, and it also has a horizontal reaction. Let's just take one look at this beam. There is no force on this beam acting to the left or right. It's all up and down. So because of that, we could just observe that Bx equals 0. So much so that I'm not even worried about it. In fact, I'll go ahead and tell you, on the homework solution, I didn't even bother talking about Bx. I don't really care. I'm just talking about the vertical reactions here. So really what I'm trying to figure out is what is Ay and what is By. Okay, and I want to show you 2 different ways we can handle this, and we end up getting the same answer. The first thing I want to do is I want to use, I think, a simple approach, which is to use the individual components. So let's go with option 1. So let's look at the components. Okay, so here's the beam, and we have a roller here. So we'll say this is AY, and we have, sorry, I got ahead of myself here. We have a hinge here, and we'll have a reaction here. We'll call it BY. Now I have this distributed load, and you can see how it's it starts at 1,500 newtons per meter, and then it linearly increases to 4,500 newtons per meter. So what I'm going to do is I'm going to split that into 2 separate components, and I'm going to do that like this. So the idea is that one component is a rectangle. You could think of it as a rectangle that has a height of 1,500 newtons per meter. And then the other component is going to be this triangular region here. And so let's see, if you're paying attention, what would be the height of this region here? $3,000, exactly right. So this is 3,000 newtons per meter. Okay, and so here's what I'm going to do. All right, let's start off with the rectangular load. Okay, so if I were to sort of, maybe, I don't know, kind of create like a little shadow where that rectangular load would be, it would be kind of like right there, and then the triangular load would kind of be like right here. Okay, let's take the rectangular load first. Okay, so I have a load that has a height of 1,500 newtons per meter, and it is spread out over a distance of 6 meters. So the first thing I want to figure out is, what is that resultant? What would be the statically equivalent resultant? And the easiest way of answering that, or looking at that, is let's just keep it simple. I have 1,500 newtons per meter applied over a beam that's 6 meters long. How much force is that? Help me out with that. If I have a beam that's 6 meters long and it has 1,500 newtons per meter, how many newtons is that? I promise that's not, it's nine. It's yeah, it's not a trick question. It's just 9,000. I have 1,500 newtons per meter times 6 meters, 9,000. And one way you can think about it is just what is the area of that rectangle? It's 6 meters wide. And if you think about how tall it is, it's 1,500 newtons per meter tall. So you're basically just computing the area of this rectangle, right? So if you're thinking about it in terms of areas, what's the area of the triangle? What would R2 be? Like if I had, a resultant for this, what would the area of that triangle be? So 0.5 times 6. So we have 1/2 times the height times the width. Remember, it's a triangle, right? 1/2 base times height. Yeah, that's easy to miss. That it's a triangle. Okay. Now, here's the kicker. In order for this to be statically equivalent, we have to ensure that not only do we have the right magnitudes, but they're at the right location. Let me ask you a question. What should that distance be? Should be 3 meters. Exactly right. That's 3 meters. Because that is where the centroid of that rectangular region should be. Exactly right. So let's extend that. What should this distance be? 4 meters, because that's a triangle. 2/3 from the small end, 1/3 from the big end. This should be 4 meters. Exactly right. And so if you understand that, now we've got everything that we need to compute the support reactions. Because again, this dimension, that dimension here, that's 6 meters. So watch this. So let's sum moments at A. We'll take those moments as positive. And what do we get? Well, we've got R1 times a moment arm of 3 meters, right? And then that moment is negative because it's generating clockwise moment at A. We've got R2 times 4 meters, and that moment is negative because it's generating clockwise moment. But then we have BY times 6 meters. That's all there is to it. So again, the idea is once we've split this up into its vector components and ensured that those vector components have the proper magnitude and location based on their centroid, then we can just apply the same principles that we did before. So we have 9,000 times 3, 9,000 times 4, so minus 27,000 minus 36,000, and then that equals minus BY times 6 meters, right? Well, what do I do here? That plus that, so 63,000 Newton meters equals BY times 6 meters divided by 6. And I get BY is 10500 newtons up. Just dividing both sides by 6. And so if I've got that, then I can sum forces in the y direction. And I can say, okay, what do I got? I've got AY going up, by going up, R1 going down, R2 going down. That's got to equal 0. So AY plus 10500 newtons minus 9,000 minus 9,000 equals 0. And so AY is 7,500 newtons up. Now, I've got another method to do this problem. But before we get into that, I want to see if there's any questions. Did I do that too fast? Everybody good? Yes, because if you're summing moments from A, how far is that load from A? Really, the way I should have drawn this, I guess, here's the beam. Here's an R1 and an R2. I had it drawn, over, like above. But again, whenever you're doing moment arms, you're talking about that perpendicular distance from the line of action to the point. And so that perpendicular distance is going to be the 4 meters. Let me show you the second option. The second option, so option 2, is to use the resultant and the centroid. Here's what I mean by that. Okay. Oh Lord, that went fast. Okay, here's what I mean by the resultant and the centroid. So we have R1 is 9,000 newtons, and its distance from A is 3 meters. We have R2 is 9,000 newtons, and its distance from A is 4 meters. So what I propose is what we do is just use a single vector R. Just use a single vector of 18,000 newtons, but where do I put that R? Well, I put that R at its centroid. And so that's going to be R1 x1 plus R2 x2 over R1 plus R2. And so that's going to be 9,000 newtons times 3 meters plus 9,000 newtons times 4 meters over 18,000 newtons. And so when you chug that out, you get 3.5. And that should be, pretty straightforward. If I have two equal vectors of 9,000 newtons, one's at 3 meters, one's at 4 meters, then the resultant should be right smack dab in the middle of them because they're equal. I propose what I can do is instead, I can model that as this. Sorry, I've got that in the wrong spot. It should be more about like that. A single 18,000 Newton vector, because that is R, And then how far is that from AY? How far is that here? That dimension is 3.5 meters. That's 6 meters. See, the first method, I treated each shape individually and I had two different vectors. Here, I only have a single vector. And I propose when you do this problem, you will get AY is 10,000, or sorry, I think it was, what was it? It was 7,500. You will get 7,500 up, and BY is 10,500 newtons up. You'll get the same answer. You know, the first method treated each force individually. The second method said, let's just collect all those into a single force and just make sure we put it at the right location, and you'll still get the same answer. And so that method works as well. Any questions? So from there, you sum, well, you won't sum the four, well, you can, but all that's going to tell you is that AY plus BY equals 18,000. You still need to sum the moments either at A or B. But what ends up happening is you're going to get, 18,000 newtons times 3.5 meters, that's negative, plus BY times 6 meters equals 0, and then you need to solve for B. I'm just saying that this equation ends up being shorter than what we had up here. What we had up here, we had the R1 times 3 meters, the R2 times 4 meters, the BY times 6 meters. Here, it's a lot shorter because we did all of the resultant figuring and the centroid figuring before we applied the equations of static equilibrium. So either one works, you'll still get the same answer. It's just another verification that this whole process of computing the centroids works and comports with the equations of static equilibrium. Did that answer your question? I mean, but you're right. We will end up summing the forces, but we also have to still sum moments as well. Okay, I'm going to go ahead and call it here. We're going to try and enter the third dimension on Friday. But that's all I have, everybody. I will see you all on Friday. Everybody stay safe, stay healthy. We'll see you then.